Section 5.2 talks about congruence of integers. So in order to be able to prove some more things, and based on our proof techniques we know, we're going to define this new, this idea of congruence. So I've included the textbook's definition, so I think it's important to kind of practice going through and reading these definitions and making sense of them. So let's go through and look at what this definition says. So given two integers, a and b, and some natural number n, we say that a and b are congruent modulo n if n divides the difference of a and b. We express this as a is congruent to b mod n, and if they're not congruent, then we write this as a is not congruent to b mod n. Okay, so let's actually see if we can figure out what this definition is talking about. So it says that two integers are congruent mod n if n divides their difference. Now, if you've dealt with congruency mod n before, this is probably not the way that you think about this definition. So let's see if we can kind of build up some intuition for what this means. So what I want to do is I want to come up with some examples of things that are congruent. So maybe we can let our n be 3. Try that one more time. Let n be 3. And then I'm going to think about some things that n divides. So what does 3 divide here? Let's actually put our 3. 3 divides 6. 3 divides 9. That should be enough. And so I want to pick a and b's so that a minus b is 6 and a minus b is 9. So maybe I can have a be 6 and b be 0. A be 7 and B be 1, A be 8, B be 2. I could have A be 9 and B be 0, and A be 10 and B be 1, A be 11 and B be 2. I also know 3 divides 3, so I could have A be 3 and B be 0, A be 4 and B be 1, A be 5 and B be 2. Okay, right, so this is the ones where A minus B is equal to 3. So what do we have here? So I have that 6 is congruent to 0 mod 3. 7 is congruent to 1 mod 3. 8 is congruent to 2 mod 3. 9 is also congruent to 0 mod 3. And 3 is congruent to 0 mod 3. And then 10 is congruent to 1 mod 3. And 4 is congruent to 1 mod 3. And 11 is congruent to 2 mod 3. And 5 is congruent to 2 mod 3. So maybe as you're looking at these, we start to notice some patterns, right? The ones that are congruent to 0 mod 3, well, that means 6 minus 0, which is just still 6, is divisible by 3. So those are all the ones that are divisible by 3. And then 7 is congruent to 1 mod 3, because 7 minus 1 is divisible by 3. So these are the ones that have remainder 1 when divided by 3. And these are the ones that have remainder 2 when divided by 3. Okay. Now I can add other things. I don't have to just have 1s and 0s and 2s here. So I know that, say, for example, when A is equal to 10 and B is equal to 4, 3 divides 10 minus 4, because that's 6. So 10 is also congruent to 4 mod 3. So I don't need either of my numbers to just be small, just to be that small remainder. But usually when we think about modular arithmetic or these congruent mod n's here, we're thinking about the fact that they have the same remainder when divided by 3. That's the sort of internal idea that we have. But it's actually kind of hard in proofs to use that as the definition, that they have the same remainder when divided by 3. So instead, the definition that we take is that 3 divides their difference, or that the difference between those two numbers is divisible by 3, or is a multiple of 3. So there's sort of this difference between the way that we think about congruence mod n and the way that we're actually going to use it in our proofs. So I encourage you to kind of think about it from both of those perspectives as we're going through these problems. So let's go ahead and see if we can prove some things with these, this new definition of congruence mod n. So the first thing we have is we're going to assume a and b are integers and n is a natural number. And I want to show that if a is congruent to b mod n, then a squared is congruent to b squared mod n. So if two numbers have the same remainder, mod n, then so do their squares. So let's go ahead and see if we can prove this. So I'm going to start with assuming my if. So let's assume that a is congruent to b mod n. And then I'll go ahead and immediately unpack that definition. So that means that a minus b is divisible by n, or n divides a minus b. I don't really need that to be on its own line, so let me pop that up here. Okay, so now, right, I'm not sure exactly what we need to do next. We need to be able to get to this fact that a squared is congruent to b squared mod n. So maybe I need to do a little scratch work down here to think about what that means. So I need to show that n divides a squared minus b squared. But I know that a squared minus b squared is just a minus b times a plus b. And I already have that n divides this a minus b. So maybe we can think about what it means up here that n divides a minus b. So that means that a minus b is equal to some n times another integer. I'm just going to call it x for x in z. And then I need to show that a minus b times a plus b is equal to some n times y for y in z. Okay, so this is giving me a clue here, right? I just need to be able to get an a plus b times that a minus b, and it's still to have that factor of n on the other side. So we can multiply by this a plus b, and that gives us that a minus b times a plus b is equal to n times x times a plus b, which is just n times x times a plus b, where that x times a plus b is an integer. Thus, since I can write a minus b times a plus b as an integer times n, n divides a minus b times a plus b. So n divides a squared minus b squared, since that's just what a minus b times a plus b is equal to. Thus, in conclusion, a squared is congruent to b squared mod n. Right, so again, I'm really just using this definition as we go through. First, we unpacked the definition of modulo, or congruence mod n, into this divisibility definition. Then I unpacked that divisibility definition into this is a multiple of definition. I knew what I needed to get to was this new divisibility, so I unpacked that also as a multiplication. So I was able to know what step to do next there. And then we just put all of the pieces together to get to our proof. All right, now it's your turn to try one of these. So I want you to see if you can prove the following. So given integers a, b, and c, and a natural number n, I want you to show that if a is congruent to b mod n, then a times c is congruent to b times c mod n. So go ahead, see if you can do that out using a nice direct proof, and we'll talk about that in class. Okay, let's do one more proof here. So let's assume that a and b are integers and n is a natural number. If 12a is not congruent to 12b mod n, then I want to show that n does not divide 12. So I could go ahead and assume here that 12a is not congruent to 12b mod n, which would mean that n does not divide 12a minus 12b. But again, showing something does not divide is much harder than showing it does divide. So because I see these negations, I don't really want to deal with them, this is probably a good situation to do a proof by contradiction. So let's say we'll proceed. Sorry, I think I said contradiction. I want contrapositive instead. So we'll proceed using the contrapositive. And you can write the contrapositive you want, but you don't have to. I'm going to go ahead and write it in this case. So i.e., that is, will show if the negation of that q, n divides 12, then 12a is equivalent or congruent to 12b mod n. That's what I want to show here. Okay, so we can go ahead and assume our if. Assume n divides 12, which remember is the negation of that q. Then, let's definition unpack. N divides 12 means that 12, what does n divides 12? Means that 12 is equal to n times b for some b in z. Then, what does it mean that that is true? So, I know that, right, this n times b is a multiple of 12, or 12 is a multiple of n, or n times b equals 12. So now where are we trying to go here? We're trying to get to the fact that 12a is congruent to 12b mod n. So I'm trying to get to the fact that n divides 12a minus 12b, or n divides, I notice there's a common factor there, 12 times a minus b, or that 12 times a minus b is some n times something. Okay, so I feel like maybe we're on the right track here, but I recognize an issue we made. When I wrote this here, I decided to use the letter b just as some arbitrary integer or some unspecified integer in z. But that's probably bad because I already have a b existing in this problem. So let me go ahead and fix that issue real quick. So I'm going to get rid of that b, which is an integer of z. And I'm going to use a letter that I made sure I haven't used yet. So maybe we should use x instead there, because x is a letter I haven't used yet in my proof. Okay, so what am I trying to do? I want to show here that 12 times a minus b can be written as n times something. But I know that 12 can be written as n times something. So then I can just multiply both sides by a minus b. So let's go ahead and try that. So 12 times a minus b is equal to n times x times a minus b, which again is n times x a minus b, where that x times a minus b is an integer. All right, so we're looking good. So n divides 12 times a minus b. So 12 divides, n divides 12a minus 12b. Thus, by that definition, 12a is congruent to 12b mod n, which is what we wanted to show. So By that contrapositive, we can conclude that if 12a does not divide 12b mod n, 12a is not congruent to 12b mod n, then n does not divide 12, which is what we wanted to show. So, right, it's really important sometimes to do this sort of background work. We can't do that as part of our proof because we're starting here with what we want to show and working backwards. But we can do that off to the side as our scratch work to help us know where to go next in our proof. So I encourage you to sort of not be afraid to go ahead and do that background work as you're working through these proofs. So I just want to say that there's not going to be a separate video on section 5.3. That's going to be a reading assignment for you. Obviously, you should always be reading the book, following along as we go, but this particular section has a lot of mathematical writing conventions. So I want you to go ahead and just take the time to read through those, really become familiar with them. And we'll talk in class. I want to know if there's any of these conventions that surprise you. So things that you didn't realize happened in mathematical writing, you didn't realize was the correct expression. So any of those we'll sort of follow up on in class and talk about those more. So I'll post the PDF of those pages from this section just to really make sure everybody has easy access to that, so you definitely read it. Please go ahead, take a couple minutes, it's only 3 pages, and then we'll talk about that in class.